Hello friends, welcome to lecture series on essential mathematics for machine learning. In the last lecture, we have seen that if two classes are linearly separable, then we can construct a error minimizing LPP whose objective value is 0. If the objective value does not come out to be 0, that implies that the two classes are not linearly separable. But if we are interested to find out the optimal separating hyperplane, then the method of finding error minimizing LPP may not work. It will give a linear classifier of course, but that may not be an optimal separating hyperplane. So, how can we find an optimal separating hyperplane? Optimal means the margin between the two classifiers, two bounding planes is maximum. How we can find out that hyperplane where the distance between the two bounded hyperplane is maximum, that is the optimal separating hyperplane. So, that comes under hard margin classifier. So, what is hard margin classifier and how we can construct an equivalent optimization problem for linear classification problem, so that we can find out an optimal separating hyperplane. So, let us discuss. Now, suppose we have patterns. Okay. How many patterns? Suppose we are having m number of patterns x1, x2, x3 up to xm, and each pattern is an element of Rn. Okay. And we are also supposing that these patterns are linearly separable. Okay. Having two classes plus 1 and minus 1. This di, this is belonging to minus 1 and plus 1. Okay, is a target value of the ith data. Therefore, there exists W belongs to Rn and B belongs to R such that. So, this W xi, W transpose xi minus B is greater than 0 for all I which are in plus 1 label class, and it is less than 0 for all I which are in minus 1 label class. We have already seen that by suitable scaling, this can be transformed into greater than equal to 1 for all I which are in plus 1 label class, and less than equal to minus 1 for all I which are in minus 1 label class. So, if you want to combine these two constraints, so these two constraints can be combined like this: di W transpose xi minus B greater than equal to 1 for all I from 1 to m, because there are m number of patterns. See, if you put di equal to 1, di is either plus 1 or minus 1, these are target, these are labeling basically. So, if it is plus 1, then this will converge to the first constraint, this constraint, if di is plus 1. If di is minus 1, then you multiply both the side of the inequality by minus 1, and this will convert to this inequality, that is W transpose xi minus B less than equal to minus 1. So, I want to say that the constraint can be converted into a single constraint of this, where di belongs to plus 1 or minus 1. Okay. Now, next is, what is our aim? Our main aim is to maximize the distance between the two hyperplanes. Okay. So, now what is the distance, what is the margin? The margin is basically 2 upon norm of W. Okay. This is to maximize. Now, it is same to say that this quantity is to minimize. Okay. Whether we are minimizing norm of W or we are minimizing norm square of W, both are same, because norm is a non-negative quantity. Okay. So, it is equivalent to say that norm square W upon 2 is to minimize. Now, how we can write norm of W square? This can be written as W transpose W. I mean inner product of W with itself, and under usual inner product it is nothing but W transpose W. So, what is the problem now? The problem is now converted into minimization of 1 by 2, this is 1 by 2 W transpose W, this is to minimize, okay, subject to this constraint, Okay. So, this constraint will come here I from 1 to m. So, now it is a very simple quadratic programming problem. In fact, it is a convex quadratic programming problem, because diagonal elements are all 1 by 2 in this case, and which is positive definite and hence convex. So, it is a, and constraints are linear of course. So, it is a convex quadratic programming problem, and we can have different algorithms to solve such type of problems. So, once we find W and B from these two, so then we can find a hyperplane which is W transpose x equal to B, and that is a hyperplane which is an optimal separating hyperplane. Now, here how many constraints we are having? Here we are having m number of constraints. If we are having m number of patterns, this m may be 100, maybe 1000, maybe 500. So, depending on the number of patterns, there we are having so many constraints. But using Lagrange duality method, we can reduce this number of constraints. So, which is computationally easy. So, what is that Lagrange duality method? Let us see. See what problem we are having here. The problem which we are having here, that is the hard margin classifier which I am calling, is P1 problem, and P1 problem is basically minimization of 1 by 2 W transpose W subject to what are the constraints? Constraint is di W transpose xi minus B, it is greater than equal to 1 and I is from 1 to m. This problem is basically hard margin classifier. Okay. Now, let us write a Lagrange function of this. Lagrange will be a function of W, B and alphas. So, that is nothing but 1 by 2 W transpose W plus summation I from 1 to m, because there are m number of constraints. Okay. Alpha I, it is 1 minus di W transpose xi minus B, because we have to write constraint in less than equal to format. So, that is why I put this side to right hand side, that is why we are having this here. So, this alpha I is here are basically Lagrange multipliers. How many Lagrange multipliers we are having here? M, alpha 1, alpha 2 up to alpha m. Okay. Now, if I want to write the KKT condition of this problem, so how can I write KKT conditions? What are the variables here? Variables are W, B and alpha I, this we have to find. So, W, B and alpha I, sorry, it is W, B and alpha I. So, first we differentiate with respect to W, put it equal to 0. So, that implies if we differentiate this with respect to W, so this is W only. Okay. Now, here if we differentiate with respect to W, so that is nothing but minus summation I from 1 to m. Okay. It is alpha I di xi, which is equal to 0. So, this implies W is equals to summation over I from 1 to m alpha I di xi. So, this is the first KKT condition. Next is you can take del L by del B equal to 0. So, this implies if you are differentiating with respect to B. So, with respect to B if you differentiate, so you will get summation I from 1 to m, it is alpha I, you are differentiating with respect to B. So, that gives alpha I di equal to 0. So, these are second KKT conditions, and of course, alpha I should be non-negative, Lagrange multipliers are non-negative, and next comes out from the feasibility condition. The feasibility condition is di W transpose xi minus B should be greater than or equal to 1, and next is alpha I times 1 minus di, alpha I 1 minus di times W transpose xi minus B should be 0 for all I. So, these are the different KKT conditions which we are having here for this problem. Okay. Now, if we write the dual of this problem P1, then the dual we can use the KKT condition to write the duals, and as I already said that if I instead of using this problem, if I use the dual of this problem, then it will be computationally easy to solve the dual of the given problem P1. So, what is the dual? So, first this is a Lagrange function which we have already defined. Okay. Then it is then the KKT conditions of problem P1 are this equal to 0, del L by del B equal to 0, that we have already discussed. The problem of the dual of the problem P1 is given by, what is a dual now? So, dual is given by this format. So, maximizing the Lagrange function subject to gradient with respect to W of L is 0, del L by del B equal to 0 and alpha is greater than equal to 0. What this means? So, dual of the problem will be the dual of the problem P1 is given by, it is maximizing Lagrange function, which is function of W, B and alpha subject to the KKT conditions, del W equal to 0, del L by del B equal to 0 and alpha is non-negative for all I. So, this problem I am calling as P2. Now, this condition I have already told you that this is nothing but, as we have already seen here, del of L with respect to W is equal to 0 is nothing but W equal to this. So, we can write it here, it is nothing but W equal to summation I from 1 to m alpha I di xi. Okay. And this condition is nothing but summation I from 1 to m alpha I di equal to 0. That is from this this constraint we are getting this thing. So, what is the objective function now? So, let us see the objective function. So, objective function is L which is W, B and alpha. It is nothing but 1 by 2 W transpose W plus summation I from 1 to m. Okay. It is I from 1 to m alpha I 1 minus di W transpose xi minus 1. Okay. Now, it is equal to 1 by 2. Okay. So, what is L? L we have defined here, it is alpha I 1 minus, okay, it is B. Okay. So, what is W? W we have seen here, W is nothing but sum from I from 1 to m alpha I di xi. So, if it is W transpose W, so that comes under double summation, summation I from 1 to m, summation j from 1 to m, it is alpha I. So, for one W I am representing by index I, for another W I am representing by index j. So, it is alpha I alpha j, as it is di xi. So, it will be di dj xi transpose xj. So, it looks a little bit complicated, but it is not if you open the double summation. So, it comes out to be a very simple expression plus this is summation alpha I which comes here summation over I. Okay. Next term is minus, it is summation, again this W you will replace W by this term, and I is already running here. So, let us suppose that for that W it is index j. So, it is I, then it is j, it is alpha I, again alpha j, then it is di dj xi transpose, and this is xj, and the last term is negative negative positive, this is B will come out, this is summation I from 1 to m, this is alpha I di. Now, this alpha I di, the sum of alpha I di from the second this constraint is 0. So, this will go to 0, this term will vanishes, then this term plus half and minus 1 will be minus half. So, this is nothing but minus 1 by 2 double summation summation over I summation over j alpha I alpha j di dj xi transpose xj, and this is plus summation alpha I over I. So, this will be the objective function of the dual problem, subject to what are the conditions, these conditions we are having here, these are the conditions. Okay. So, here also we did the same thing and we obtain after simplification which we have discussed. So, this will be the dual will be given by this problem. So, this constraint we have already used, you see here this constraint we have already used. So, this is the only constraint which is remaining. So, maximizing this function subject to this constraint and alpha I non-negative. So, now if we leave non-negativity restriction, then instead of m number of constraints what we are having in the primal quadratic programming problem, here we are having only one constraint. So, that is the main important application of duality theory here in this machine learning, here in this support vector machines. Okay. So, computationally it reduces so much time and of course, memory also. So, the above problem has only one constraint apart from the non-negativity constraint. Also the maximizing, here we are maximizing this function. So, maximizing a concave function and thus P 3 is computationally easier to solve. The optimal solution alpha bar of P 3 will give the values of W bar and B bar, and thereafter separating hyperplane W transpose x equal to B bar can be determined. So, in this way if you are interested to find out the optimal separating hyperplane which is W transpose x equal to B. So, after solving this dual problem we can find alpha bar, and using alpha bar from this we can find W bar, okay, and then from the other conditions we can find B bar, from which we can find W bar transpose x equal to B bar, which is the optimal separating hyperplane. Now, let us discuss one example. So, here we are having two classes again -1 and +1. So, these are the points 2 1, see 2 1, this is 1 2. So, these square boxes are the patterns in -1 class, and these circular boxes, circular patterns are the patterns from +1 class, and these of course, these are linearly separable. Now, if I want to find out the optimal separating hyperplane, so we have to construct a convex quadratic programming problem. So, how can I construct a equivalent convex quadratic programming problem? So, let us see what are the patterns we are having here. So, patterns for A minus R, 1 2 2 1, three 2 and 2 3, and patterns for A plus R, 5 4 4 5, then it is 5 6 6 5. So, these are two classes we are having here. So, what is the equivalent QPP? That will be minimizing 1 by 2. So, all the patterns are in R2. So, W will belongs to R2. So, that will be W transpose W, that means W1 square plus W2 square, okay, subject to what are the conditions. Conditions will be, so condition we already know, see what hard margin classification problem we are having, 1 by 2 W transpose W subject to di W transpose xi minus 1 minus b greater than equal to 1 I from 1 to m. Okay. So, if di is minus 1, because for this it is minus 1. So, it is negative of w1 plus 2 w2, because first pattern first xi x1 is 1 and 2 and this w is w1 w2. So, w1 w2 will multiply with 1 and 2. So, it will be w1 plus 2 w2, it is a simple matrix multiplication, and this is minus b greater than or equal to 1. The second constant will be minus of, second pattern is 2 1, you substitute 2 1 here. So, this will give 2 w1 plus w2 minus b greater than or equal to 1. This is minus 3 w1 plus 2 w2 minus b greater than or equal to 1. This is minus 2 w1 plus 3 w2 minus b greater than or equal to 1. Now, come to the plus patterns for plus 1 class. So, it will be di will be plus 1. So, that will be nothing but 5 w1 plus 4 w2 minus b greater than or equal to 1, 4 w1 plus 5 w2 minus b greater than or equal to 1, then it is 5 w1 plus 6 w2 minus b greater than or equal to 1, then it is 6 w1 plus 5 w2 minus b greater than or equal to 1, and of course, w1, w2 and b are unrestricted. So, this is the basically problem P2 problem we are having now. So, we can solve either this problem or we can write a dual of this problem using this formulation. We can add a dual and we can solve either of the problem, either this problem or the dual. Okay. So, if you solve this problem, so we will get, these are the constraints. So, we will get, you can use any solver to solve this problem. So, we will get w1 equal to w2 equal to 0.5 and b equal to 3.5. Hence, the equation of the plane will be w transpose x equal to b, which is 0.5 x1 plus 0.5 x2 equal to 3.5. So, this is basically the optimal separating hyperplane where margin is maximum. So, this plane is basically x1 plus x2 equal to 7, okay, which is the optimal separating hyperplane. So, we have seen that if you are having, if you are interested to find out an optimal separating hyperplane, so that the error minimizing LPP may not give the optimal separating hyperplane. If the two classes are linearly separable, then we can use hard margin classifier. So, what this problem is? In this problem, we will try to maximize the margin by formulating an equivalent quadratic programming problem. That quadratic programming problem is also convex. So, using KKT conditions and duality theory, we can also construct an equivalent dual of the given problem, given quadratic programming problem. So, the problem can be solved either by the formulating the QPP or by formulating its dual. It is always computationally easier to use duality approach because it reduces number of constraints significantly. So, thank you.